In software engineering, there is a predictable life cycle for complex systems. They begin as monolithic codebases. As operational demand scales, those monoliths become too heavy to maintain, and they inevitably fracture, requiring engineers to decouple them into independent, specialized services. We saw this pattern in the 1970s. Early applications tightly coupled their logic and their data storage. To scale successfully, engineers extracted the data layer entirely, creating standalone database systems. In the 1980s, the cycle repeated. Code bases were stripped of routing logic to create dedicated workflow process engines. By the 1990s, organizational hierarchies were externalized into distinct identity and access management systems. Today, we face a similar architectural bottleneck with artificial intelligence. Legacy systems relied on a structure where human users drove the process and AI merely assisted. Modern AI agents, however, are action-oriented systems designed to execute tasks autonomously. To survive the transition to full agentic autonomy, enterprise architecture must follow its own historical pattern. We must extract human oversight logic from the application itself. Currently, developers are building human-in-the-loop approval gates backward. They are writing rigid conditional rules directly into the individual workflow of the agent. Because this oversight logic is embedded inside the application, engineering teams are forced to duplicate their code across every single new agent node they deploy. Distributing these checkpoints across dozens of isolated workflows prevents an enterprise from enforcing uniform governance. A policy change to financial approval thresholds has to be manually tracked down and updated in every separate node. But the architectural friction is secondary to the security risk. Large language models are inherently non-deterministic. The von Neumann architecture that powers traditional computing relies on a strict separation between executable code and the data it processes. In an LLM, that boundary is obliterated. Plain text prompts act as the code, dynamically steering the system's control flow. If your human-in-the-loop mechanism is just a hard-coded instruction asking the agent to pause for approval, you are relying on the LLM to police itself. A clever prompt injection attack can easily bypass that instruction. An effective security boundary must sit entirely outside the non-deterministic engine. It requires verifiable, external code that controls execution permissions. Leaving human oversight embedded inside the agent workflow creates an unscalable security liability. Solving this requires a radically different framework. The solution is to decouple the human-in-the-loop logic, externalizing it as a centralized, independent system component. Under this model, the agent workflow focuses exclusively on task execution. When it encounters a decision point requiring human input, it delegates the interaction routing to the shared service. This separation is mediated by a standardized RESTful API. It creates a clean, auditable bridge between the autonomous machine and the human overseer. When an agent hits a risk threshold, it calls the /API/HITL/request endpoint. This transfers the entire decision context and the control payload away from the agent. To retrieve the human's decision, the agent can use a polling execution mode via /API/HITL/getDecision. This method allows the agent to remain stateless, making it highly effective for deployments operating within restricted local networks that block inbound traffic. Alternatively, the agent can provide a callback endpoint in its initial request. The service then delivers the human's decision asynchronously, enabling highly responsive, event-driven integrations. Consolidating these interactions behind a single API eliminates rewriting approval logic for every new deployment. Governance policies are defined once, centrally, and applied everywhere. By enforcing standard interfaces, human oversight graduates from a fragmented application feature into a unified infrastructure-level control plane. A centralized control plane cannot ask a human to review every single action, or the system grinds to a halt. The service uses a four-dimensional execution model to dynamically compute interventions. The first dimension is when, defining the specific intervention conditions. This illustrates an event-driven system. An agent evaluates its proposed action against a strict risk rubric. The moment confidence drops or financial impact crosses a defined threshold, the service triggers an alert. This leads to the second dimension, who, or dynamic role resolution. Hard-coding user IDs into an agent's code guarantees failure when employees change roles. Instead, the control plane resolves the required human at runtime by querying organizational metadata. If an enterprise restructures, compliance approvals automatically route to the correct new officer. This maintains mathematical separation of duties without requiring a single line of agent code to be rewritten. Defining the when and who guarantees human attention is treated as a highly targeted resource, avoiding the alert fatigue that plagues poorly designed systems. The third dimension determines the what, the interaction semantics. Not every intervention is a binary approve or reject gate. Semantics can range from simple read-only auditing notifications to complex requests where a human must provide rich contextual modifications to an agent's drafted plan. Finally, the fourth dimension is the where, dictating the protocol-level routing of the request. By separating the communication channel from the workflow logic, the control plane optimizes delivery. A high-risk, time-sensitive escalation can ping a manager's phone directly via Slack, while routine performance digests are batched and routed asynchronously to an email inbox. We can see this framework operate in a typical email agent triage scenario. This flowchart shows the agent parsing incoming messages, identifying intents, and hitting the approval decision gate. When the agent detects an unusually large client inquiry, it satisfies the when condition. The service resolves the specific account manager for the who, requests modifications to a drafted reply for the what, and routes the alert to Telegram for the where. This architecture extends beyond theoretical design. These four dimensions map directly to emerging agent-to-agent protocol standards, like the Model Context Protocol. Here, we see the parameters explicitly defined in the JSON schema mappings. Translating these dimensions into a standardized schema permits that complex organizational governance can be executed reliably as an interoperable protocol-level function. An autonomous agent executing financial transactions or querying secure databases requires an impenetrable barrier between its reasoning engine and its execution capabilities. This introduces the concept of a deterministic last line of defense. Because the decoupled architecture operates outside the agent environment, it provides hard protection boundaries built on conventional, verifiable code. It is completely isolated from the LLM's non-deterministic logic. If an LLM hallucinates an instruction to delete a critical file, the request still has to pass through the external API. Strict validations, rate limits, and tool allow lists block the prohibited action, regardless of the prompt that generated it. In multi-agent environments, centralizing this service prevents privilege escalation. A low-clearance agent cannot trick a highly privileged peer into executing a sensitive action because the central control plane verifies authorization independently. Safety requires a deterministic infrastructure layer that governs execution permissions independently of the agent's reasoning. Establishing this control plane is the prerequisite for the ultimate operational goal of enterprise AI, progressive autonomy. Funneling all human-agent interactions through a single decoupled service generates a massive, unified dataset of enterprise-wide collaboration patterns. Analyzing these interaction logs reveals exactly which decisions the AI handles flawlessly and where it consistently requires human correction. This line graph demonstrates the path to autonomy. As an agent proves its statistical reliability over time, administrators safely adjust the when dimension. They lower the risk threshold, meaning the volume of autonomous action scales up, while the frequency of human interventions drops. The systems autonomously learn to dial down human requests for low-risk, routine scenarios. This continuous, data-driven tuning process ensures efficiency without compromising safety. Human oversight is explicitly reserved for high-risk, uncertain edge cases, where contextual judgment is actually required. This model offers a stark contrast to the monolithic systems we examined earlier, where embedded logic creates brittle, unscalable bottlenecks. The decoupled model adapts and scales dynamically. Human-in-the-loop oversight functions as the essential infrastructure control plane required to safely accelerate enterprise systems toward full autonomy.